Okay, so this week we talked about other types of L'Hopital's rule problems, a couple approximations, and the extreme value theorem. But before we get into worksheet 9, there was one problem from worksheet 8, problem 4b, that we didn't finish. Well, that we didn't do. So here we have 4b. We have a rocket is being launched here. 3 miles from the launch site, there is a radar station, which has a camera focused on the rocket. Has is H-A-S, not H-A, as is written. When the rocket, the question says, the question asks, how fast is the angle between the camera and the ground changing at this time? At what time? When the rocket is 100 miles above launch site. Well, let's translate that question into calculus. How are we going to translate that? Where is it? How fast is the angle changing? Well, first, we still have these variable quantities as we had in part A. We have X and Y. Those are both changing. 3 is not changing. But we also have the angle theta, which is changing as the rocket goes up. Question is asking, find d theta dt. When does it want d theta dt? Well, let's see. When the rocket is 100 miles above launch site. So when x equals 100, we might need y. We probably will need y. We will need y. Well, we'll see when we need y. It's not obvious right now when we need y. When x is 100 and its velocity, so this rocket is going upward, so its velocity is measured by x. So and dx dt was what? What was it? 600. And our units are miles, hours, and miles. So we need d theta dt. So we need a relation between theta and our variables. It may be tempting to use sine of theta, because sine of theta is x over y. But if you use sine of theta, you're going to have an equation with 3 variables. And dealing with that is much less convenient because you'd have to solve for one of them using Pythagorean theorem. A more convenient relation we can use with theta is using theta and the 2 legs, because one of the legs is constant. So here we have theta and the 2 legs. You could use cotangent. I'm going to use tangent because tangent of theta, tangent is opposite over adjacent. So tangent of theta is x over 3. Now, we have a fraction. Let's just get rid of the fraction. Now it's all written in one line. So we have tangent of theta is x over 3. Just put 3 on the other side. We have 3 tangent theta equals x. And this is the equation we're going to differentiate with respect to time. X, y, which isn't showing up yet, and theta are all changing as time is changing. So we'll differentiate with respect to time. Any questions about finding that equation? If you use sine, you'd get what? You'd get like x over root x squared plus 9, and then you have an annoying quotient rule to deal with. But here we'll just use tangent because fewer variables, fewer numbers, and it'll be easier. So what are we going to do? Differentiate with respect to time. And what do we get? Where should I write this? I guess it'll fit here. 3 carries through. Tangent of theta. What's the derivative of tangent of theta? Secant squared of theta. But then we need the chain rule. Derivative of... Okay, so if you're taking notes, you probably wrote this sentence down. I'm going to have to erase it to illustrate everything I want. Remember, the derivative of tangent of something is secant squared of that same thing but then you use the chain rule, multiply by the derivative of that thing. So here we have a theta on the inside. We're going to have to multiply by the derivative of that theta with respect to time. So secant squared of theta times the derivative of theta. The derivative of tangent will always take that form. Any questions about the left side of that equation? Okay, and the right side of that equation, derivative of x with respect to time is 1 times dx dt. Well, so we wanted to solve for secant or for d theta dt, so we can do that. D theta dt is what? Yeah, okay. Not 3, sorry. 1/3. So you could substitute and then solve. I'm going to solve and then substitute. Divide by 3. Divide by secant squared, which is the same as multiplying by cosine squared of theta. Wow. Right, maybe I should slow myself down. So solve for d theta dt, divide by 3, divide by secant squared, same as multiplying by cosine squared, times dx dt. What is cosine squared of theta? Well, cosine of theta is what? 3 over y. What's y? Well, we're going to have to do some simplifying to figure this out. So we have 1/3, we have cosine theta. What was dx dt? It was 600. So we're going to need a number between them. How do we find cosine? Well, how do we find cosine of theta? And then how do we find cosine squared of theta? So I'm going to fill that in here and then write the answer here and do side work here. So to find cosine squared of theta. Well, we're considering this triangle when x equals 100. When x equals 100, that side is 100, that side is 3. What's cosine? Cosine is adjacent over hypotenuse, so we need the hypotenuse here. What's the hypotenuse? Well, 100 squared is 10,000, 3 squared is 9, 10,000 plus 9 makes 10,009, and we need the square root. I don't think a number comes out. I don't think a number comes out. Don't worry if a number comes out of a square root. That's not a useful simplification. I believe it does. I believe I set it up so that it doesn't. But what's cosine of theta now? Well, cosine of theta adjacent over hypotenuse. So cosine squared is that squared. So 9 over 10,009. Putting that up here, cosine squared, 9 over 10,009. Any questions about finding cosine squared of theta? So notice we did need to eventually figure out something about the hypotenuse, even though it didn't show up in our equation. So any questions about finding cosine squared? That last fraction doesn't reduce because 10,009 is not divisible by 3 or 9. So now we just have to write this as one fraction. How did I do that? Well, is that a question? If that's a question, I can't understand anything that's being
Because all
said.
of a sudden you realize, wow, I can help my church. I can help the local school. I can help my kids. I can help my mom.
Okay, thank you. Okay, that was faster than trying to find whoever's talking to me. So, what I did here was I did 600 divided by 3 is 200. 200 times 9 is 1800.
Why? Did I not?
So any questions about this number 4b? I guess I should throw units on it. Radians per, oh no, our units are, oh yeah, radians per hour. So any,
I joined a
questions?
little late. What problem on the worksheet was 4B?
oh, this was the worksheet from last week.
Oh yeah. 'cause
So
we
last
finished
week
it.
we didn't
Yeah.
cover problem 4b.
All right.
I pushed it off until this week. So this was worksheet 8. Yeah. So any other questions about this one? Okay. So let's go on to this week's worksheet. So this week, we discussed L'Hopital's rule, some approximations, and the extreme value theorem. Last week we began L'Hopital's rule, and this week we extended it to some other types of limits. 1a, limit x goes to 0 from the right, 3x plus 1 to the cotangent of x. So first, if you could do a substitution and get a number, then that is your answer. So you should always check if you could do a substitution. And what happens if you do a substitution here? Well, you get 1 to the cotangent of 0 as x approaches 0 from the right. I'll just use that notation. Cotangent of 0. What is that as x approaches 0 from the right? Well, cotangent is cosine over sine. What happens when you substitute x equals 0 into cosine over sine? Well, you get cosine of 0 over sine of 0. Gives you 1 over 0. What happens when you get 1 over 0? Well, you look at both sides of 0, you get an infinity or a negative infinity. Here we're on the right of 0. On the right of 0, we can interpret that with angles. In the first quadrant, everything's positive. So that limit would be a positive infinity. In other words, upon direct substitution, taking the limit directly, you would get a 1 to the infinity. 1 to the infinity, something, limit as x goes to infinity, 1 to the x is not 1. It can take the form of any number. But what we can do is use a logarithm to turn this into a limit on which L'Hopital's rule applies. So let's do that. Am I going to have room for that? Maybe I should have written that a little smaller. Yeah, that's fine. Which one is this? Yeah, this should fit. So equals, and I'm going to do side work because we're going to compute a different limit to figure this out. We compute which limit? Limit as x approaches 0 from the right of the logarithm of this. If we introduce a logarithm, we can then use logarithm properties in algebra to get this into a form on which L'Hopital's rule does apply. And then to find this limit, we can take e to everything and get rid of the logarithm. So first, cotangent comes out front. we have this multiplication. Now, all we did here was write this in an infinity times 0 form. And with these, with one of the 3 forms discussed in lecture, they will all turn into an infinity times a 0. And what we have to do is write that as a fraction. And here we have cotangent x and logarithm of something. I find it easier to put the trig function in the denominator than the logarithm. So remember, L'Hopital's rule applies to limits of certain quotients. So I'm going to leave the logarithm in the numerator and put cotangent in the denominator. So we would have 1 over cotangent. But remember, 1 over cotangent is the same as tangent. Any questions about rewriting this in this fractional form? Maybe I won't have room for this. Now, why did we do that? Well, now if you do a direct substitution, you'd get log of 1, which is 0, over tangent of 0, which is 0. And on that 0 over 0 form, L'Hopital's rule does apply. And what does it equal? Well, it equals this limit. Derivative of the top. Well, remember, the derivative of a logarithm is 1 over 3x plus 1 times the derivative of 3x plus 1. So 3 over 3x plus 1. Derivative of tangent is secant squared of x. So we have this fraction now. Any questions about that? Well, sorry, that should say 0 on the right. We're only on the right of 0 because we have a logarithm. Well, actually, in this case, because of the cotangent, not because of the logarithm. Only matters a little. So how can we compute this limit? Well, can we compute the limit? Well, we can. I'm just debating where I want to. I guess I'm going to go right here. I don't want to write on the wall. So how can we compute this limit? Well, you could do a direct substitution there. You could get rid of the 3-tiered fraction. I guess I'll get rid of the 3-tiered fraction and then do a substitution. Divide by secant squared. That's the same as multiplying by 1 over secant squared, which is the same as multiplying by cosine squared. Or you could do the substitution down there. As x goes to 0, we have 3 cosine of 0, which is 1 over. So let x go to 0. Cosine of 0 is 1. That ordered pair is 1, 0. And the bottom goes to 3 times 0 plus 1. So we get that this limit is 3. Well, we get that the limit that we computed is 3. Any questions about the side work? All that side work tells us that the limit we want is e to this number, which is e cubed. Any questions about part A? So this one was a 1 to the infinity form. The next 2 are 0 to the zeros. So let's do part B. Now, I posted on Canvas 2 additional L'Hopital's rule problems that I worked through. The algebra and the calculus in the 2 I posted are more complicated than the ones we covered. And I would say parts B and C fall kind of between the 2 I posted in terms of difficulty. And we'll see why in a moment. X to the sine x. Now, on your homework, I believe you have sine x to the x. That's not your homework. Where did I put your homework? Yes, you have sine x to the x. Here, we have x to the sine x. X to the sine x is more difficult than sine x to the x in terms of the eventual simplification. You can't use this to find the limit on the homework by like flipping an exponent and a base around. Well, flipping the exponent and the base around for your final answer. But what do we get upon substitution here? 0 to the sine of 0, which is 0 to the 0. While 0 to the 0 is not a number. It is an indeterminate form, but to compute this limit, we can introduce a logarithm. So throw a logarithm on that and bring the sine x out front, and it turns into this product. This limit is a 0 times negative infinity form. And we can compute this by putting something in the denominator. I'm going to put the trig function in the denominator. In general, the algebra works out more nicely if you leave the logarithms in the numerator. So we have log x in the top. And what do we have in the bottom? 1 over sine x, which is also known as cosecant of x. As x approaches 0 from the right, this one is a negative infinity over a positive infinity. And L'Hopital's rule applies to that. L'Hopital's rule applies to that. Remember, L'Hopital's rule applies only to fractions which take a form 0 over 0 or infinity over infinity, positive or negative. Derivative of log x, 1 over x. Derivative of cosecant x is negative cosecant x cotangent x. Any questions about getting here? Now, if you try a direct substitution here, you would get, what would you, like an infinity over an infinity with either a positive or a negative sign. But is there something we can do to simplify this? Well, we have reciprocals of trig functions. Let's write this as one fraction. So 1 over x, it's 1 over x times 1 over cosecant x cotangent x. Well, that's the same as one over x times sine x, oh, there's a negative, times sine x times tangent x with a negative somewhere. So we can rewrite that fraction as this fraction. Now, again, if you do a direct substitution, you get a 0 over 0. With that, I suppose you could do L'Hopital's rule, and then you'd have a product to deal with. That should work. I'm not going to do that, though. I'm going to do it a different way, without applying L'Hopital's rule. because notice we have a sine x over x. I'm going to split this limit into two, which we can do because both of these limits exist. We saw in week, I believe, 3, when we covered squeeze theorem, that the limit as x approaches 0 of sine x over x is 1. You could also use L'Hopital's rule, get cosine x over 1, which as x goes to 0 is 1. So that limit is 1. As x approaches 0, tangent x approaches 0. We saw that in the last problem. Negative 0 is 0, and then 1 times 0 is 0. So here, we use L'Hopital's rule, and then we wrote it as one fraction. Then we used a convenient week 3 limit. You could have gone from here and done a another L'Hopital's rule with a product rule, but I didn't want to deal with the product. So that limit is 0. So this limit is e to the 0, which is 1. Any questions about part B? Part C, what do we have? X plus sine x to the x as x approaches 0. X plus sine x to the x as x approaches 0. Again, this takes a 0 to the 0 form. And we can compute that by introducing a logarithm. And I always like writing this immediately at the beginning, just so when I look at the problem at the end, I don't get tempted into thinking that that's the final answer. I guess I didn't make that mistake on a test in a class like this, but on a homework that I submitted back when I took it, I didn't take E at the end, and I lost a point. Well, actually, I think I lost more than 1 point because that professor liked large deductions. But we have a 0 to the 0 form. I think it was a 3-point mistake on like a 5-point problem. It was really annoying. So we have here a 0 to the 0. We can compute this by introducing a logarithm and then using L'Hopital's rule. So we compute the limit as x approaches 0 from the right of the logarithm of that. The exponent x comes out front. We have now a 0 log 0 form, 0 negative infinity. We can compute this by putting that x in the denominator. And leaving the logarithm in the numerator. Put the x in the denominator, becomes a 1 over x. Because this right now equals that. As x approaches 0 from the right, this is a negative infinity over n infinity. Log 0 as x approaches, well, log x as x approaches 0 from the right, negative infinity. And this denominator goes up to positive infinity. And L'Hopital's rule does apply. Now, what do we get? Well, this is one of those limits where having a couple shortcuts in mind helps future simplification. Denominator, derivative 1 over x, negative 1 over x squared. What about the numerator? Well, remember, the derivative of a logarithm is 1 over the inside times the derivative of the inside. So derivative of the numerator, derivative of the inside is 1 plus cosine x. Derivative of the inside. So we get 1 plus cosine x over x plus sine x in the top, and then negative 1 over x squared in the bottom. And right here, we have a 4-tiered fraction. Let's make that a 1-tiered fraction. Well, 2-tiered fraction, I should say. A 1-tiered fraction, the whole number. So I'm going to put that negative 1 over x squared in the top. And what does it become? You could factor out a negative. Well, I already started writing like this, so I'm not going to. So divide by negative 1 over x squared. That's the same as multiplying by negative x squared over 1. And I distributed the negative x squared through the numerator. Now, this limit doesn't look necessarily easier than previous limits. And sometimes with L'Hopital's rule, you can get trapped in applying L'Hopital's rule, making the problem more complicated. And this looks like that may be happening. But what happens if we try to compute this limit? Well, as x goes to 0, you get 0 on top, you get 0 on the bottom. L'Hopital's rule applies. So I don't have room to write this under, so I'm going to go up. 0 over 0 form, L'Hopital's rule applies. Derivative of the bottom, one plus cosine. What about the derivative of the top? Well, negative x squared, derivative of that is negative 2x. But the other thing, we're going to need a product rule on. Derivative of x squared is 2x with a negative on it. Derivative of cosine is negative sine. So for this product rule, what did I do? I treated the two pieces as negative x squared and cosine x. Derivative of negative x squared is negative 2x times the second plus the first times derivative of the second negative sine x, and those negatives make a positive. Well, we're at this stage, and it looks like applying L'Hopital's rule made this much more complicated. But notice what happens when you substitute. The top, you get 0, 0, and 0. What do you get on the bottom? Cosine of 0 equals 1. Because that point is 1, 0. So on the bottom, you get 1 plus 1. 0 over 2 is 0. So the side work limit was 0. The overall limit is then 0, which is 1. So are there any questions about these three? I would say all three of these were more challenging than the ones we covered in the lecture. But, especially one like this, all the derivatives we've done, if you can use a couple of the shortcuts we did, like the logarithm one, it makes the simplification much quicker. So any questions about number 1? So number 2. If you see me looking in that direction, it's because someone walks by outside, and if someone walks by, I'm always tempted to look. Where are we? Number 2. Find the linear approximation. Numbers 2 and 3 use the linear approximation. And the linear approximation is a result of following the tangent line. So the general equation for the linear approximation is a rewriting of an equation for a tangent line. What am I writing? Wait, we used A. Sorry. And a year ago, I used X instead of A. We used A this semester. So we have this equation, this rearrangement of an equation for a tangent line. And we can use this to approximate a value we don't know using a function evaluated at a value we do know. So here for number 2, we're trying to approximate the cube root of 8.1 squared. Well, the cube root of 8.1 squared is going to be close to the cube root of 8. Do I say what a value? Oh, look at that. I even wrote near x equals 8. I guess that should say near a equals 8 because that's the letter I used in the lecture. I hope that didn't confuse anybody. I'll remember that for the test that we used the letter A. This question should be phrased near a equals 8 if I give you the a value. But we know the cube root of 8 squared because the cube root of 8 is 2. 2 squared is 4. So in this case, we have the function x, cube root of x squared is also x to the 2/3. We can apply power rule to that to find the derivative. F prime 2/3 x to the negative 1/3. Here, the value we know is a equals 8 or x equals 8. So evaluating this at 8, 8 to the 2/3 is 4. Cube root of 8 is 2. 2 squared is 4. The derivative evaluated at 8 is what? Well, it's 2/3. 8 to the negative 1/3. Well, the cube root of 8 is 2. The negative just says take 1/2 instead of 2. And then the 2's cancel. So we get 1/3. So all of this was using the value we know. Now, how are we going to use the value we know? Well, we have this nice equation. Here's our starting point. We know the approximation is going to be close to 4. How close to 4? Well, this close to 4. Derivative at 8 is 1/3 times x minus our a value, which is 8. So right here is the linear approximation. You don't have to simplify that. That's if you simplify this, distribute and combine the numbers, the next simplification becomes more inconvenient. But here, we want this at 8.1. 4 plus 1/3. 8.1 minus 8. 8.1 minus 8 is 1/10. So we have 1/3 times 1/10. So 4 plus 1/30. And for a linear approximation, that type of answer is fine because it conveniently illustrates that our answer is a little larger than 4. But if you wanted to write it as one fraction. So, whichever answer you'd prefer to give is fine. Any questions about 2? So in number 2, I did tell you in the directions, the function and the convenient value. Another phrasing could be like problem 3, where you need to figure out the function and figure out the convenient value. But it will still use the same linear approximation formula. So here, in number 3, we're going to approximate sine of 29 degrees. Well, sine of 29 degrees. We haven't seen degrees much. But remember, from a 30, 60, 90, pi over 6, pi over 3, pi over 2 triangle, we can easily find, using the triangle, the sine of 30 degrees, the sine of pi over 6. So what we're going to do is use a linear approximation near this value we know. We know this. What is it? It's a half, I think. So to set up our linear approximation, we're going to let f of x be sine of x near a equals, well, in getting it in the linear approximation form, we're going to need the radians because we want those units to match up. So 30 degrees is pi over 6. Yeah, I'll leave it as pi over 6 for now. So f of x is sine of x. F prime is cosine of x. We need to evaluate at pi over 6. What's sine of pi over 6? Well, let's draw our triangle. Pi over 6, pi over 3, pi over 2, 1 to root 3 to 2. Sine is opposite over hypotenuse, so a half. Cosine for f prime of pi over 6. Cosine is what? Adjacent over hypotenuse. So we have f of pi over 6 and f prime of pi over 6. And we can use this to find our approximation. Any questions so far about this?
Shouldn't I don't know if this even matters, but you wrote sine of x. Doesn't it make more sense if it was sine of a, or does that just not matter?
Well, this right here is a general function. We're evaluating at a here. So technically this would be sine of a, but the general function is in terms of x, and we're evaluating at pi over 6. So like in this linear approximation formula, I'm jumping over all these x's and just using these values. So here, fx pi over 6 is a half plus f prime at pi over 6, which is root 3 over 2 times x minus a. Well, I'm going to look ahead a little and realize writing pi over 6 in terms of its unsimplified conversion is going to be eventually more convenient. Now, why is that? Well, because we're evaluating this at 29 degrees, which remember in radians, multiply by pi over 180, degrees go away. 29 pi over 180. Wow. I guess I wrote it like this before. So L at that is a half plus root 3 over 2. Let x equal 29 pi over 180. And now what's inside those parentheses does simplify. Well, it doesn't combine nicely into what? Negative pi over 180. And I guess this can all be written as one fraction. I'm just going to write it like this. A half minus root 3 pi over 360. Yeah, you could do 180 minus root 3 pi all over 370, and I'll just leave it like this. That's fine. That's not the important simplification going from here to. But the observation here was that we needed to approximate sine of 29 degrees. We knew sine of 30 degrees, so we could use that. Any questions about number 3? Okay, number 4 uses our differentials approximation, which is very related to the linear approximation, but it is a little different because it only looks at that piece of the linear approximation. The radius of a cylinder with height 4 is measured as something with some area. Use differentials to estimate the error in using these values to compute the surface area of a cylinder. Well, we need the surface area of a cylinder. And last week, I posted a document with the surface area of a cylinder. The surface area of a cylinder can be broken into the circle on top, the circle on the bottom, and the rectangular side. The circles have area pi r squared. The rectangular side, the height is h. The other side is the circumference of that circle, which is 2 pi r. So we have pi r squared, and 2 pi r h. So our surface area is 2 pi r squared plus 2 pi r h. There's our general surface area. What does this problem tell us? Well, this problem tells us the height is always 4. If the height's always 4, well, you can substitute 4 there and get rid of one of our variables. Let h equal 4, that makes it 8 pi r. And this says the radius is 3 inches with an error of at most 0.1 inch. Differentials will take the most, the largest error, and use that in the approximation. So here we're going to use differentials. I'm just going to call it capital S, not SA. Now, if you take Calc 3, surface area shows up like halfway through the semester, and they just use capital S for it. So I'll just use S for it here. But the differentials approximation says we can approximate an error in surface area using the derivative with respect to radius in this case, and factoring in the error in radius. And how do we do that? Well, the derivative here is 4. So derivative there is 2r times 2 pi gives us 4 pi r. Derivative here, we have a constant. Derivative r is 1. So 4 pi r plus 8 pi all times dr is our differentials equation. The derivative with respect to r times the error in r. Let r equal 3. And what do you get? 12 pi plus 8 pi times the error, which is a 10th. So you get 20 pi over 10, which is 2 pi. That's a terrible pi. So you get 20 pi over 10, 2 pi. Technically, to be completely technical, you could say that it's a positive or a negative because it could go in either direction. I'm okay with just the positive because, well, I'll just leave it. I'm okay with just taking the positive because if you're actually thinking about the error, you can think, well, it goes 2 pi above, 2 pi below. That answer's fine with me. Any questions about number 4? Okay, so number 5. Number 5, we have a couple extreme value theorem problems. And remember, the extreme value theorem tells us on a closed and bounded interval, a function will always achieve an absolute maximum and an absolute minimum. And to figure out what it is and where it occurs, we need to find all points where the derivative is 0 or undefined if you have, like an absolute value type function. But you also need to find the endpoints, because if you chop off something like this and look at only this piece of this function, well, the highest it gets is on one of the endpoints. Now that drawing was kind of a summary of a half-hour lecture. But what do we need to do for a problem like this? Well, we need to find the derivative, find where it's 0, find where it's undefined, find the endpoints, compare the function at all of those points. So part A, what do we have? We have f of x is a third of x cubed, -9 of x, and 1. And our interval is -2 to 5. Well, we need the derivative, we need where it's 0, we need where it's undefined. Let's take the derivative. 3x squared times a third is just x squared. This derivative, -9. We want to set this equal to 0. It's 0 when x is +3 or when x is -3. It's never undefined because it's just a polynomial. So we have all points that we need to consider. Notice the derivative is 0 at -3, but let's knock down a pile of papers. But we're only looking inside the interval -2 to 5. So all that matters is what happens to the function inside there. What happens over here at -3 doesn't matter. So to figure out the absolute maximum, absolute minimum on this interval, all we need to consider are the 2 endpoints and +3. So let's do that. At -2, we get what? -8 thirds plus 18 plus 1. What is that? 49 thirds? -8 thirds, so it's 19 minus 8 thirds. 19 is 57 thirds. 57 minus 8 is 49. So we have 49 thirds. Well, we need the other values. At 3, well, that's convenient that 3 cancels and you don't have a fraction here. A third times 27 is 9. Minus 27, 9 times 3, plus 1. So that's -17. And at 5, what do we have? 5 cubed is 125. 9 times 5 is 45. And there's a negative. Plus 1. So what does this equal? It equals 125 thirds minus 44. 44 times 3 is 120 and 12, 132. 125 minus 132 gives us -7 with a denominator of 3. So we did all of this work, but we need to reach our conclusion. We need the absolute maximum and the absolute minimum. Here, I don't have much room to write it. So in the lecture, I concluded these with a sentence. I guess here I'll just say, which one is the largest? Well, that's the only positive one. So there's our absolute maximum. Which is smaller? Well, that's almost 0. That's pretty far from 0, so that's the smallest. So that's our absolute minimum. And it occurs at -2, the other occurs at 3. Any questions about part A? What was our interval here? -1 to 1. We have now this function. Again, we're going to need its derivative where it's 0, where it's undefined. So what do we get? Well, to find the derivative, we need a product rule. Derivative of x is 1. So we have 1 times the second plus x times derivative of that first one. Where did that come from? Well, derivative of √1 minus x is that, but you need to multiply by the derivative of this inside, by the chain rule. Derivative of 1 minus x is negative, so that makes it -x. And then the x carries through with the product rule. So we need, well, any questions about that derivative? We need where this is 0, where it's undefined. I find it most convenient to write this as just one fraction, because then we just have to set the top and bottom equal to 0. So the common denominator will be 2 √1 minus x. What will the numerator be? Well, to get this on the denominator over here, we need to multiply by 2 √1 minus x. So the numerator So on this first piece, we need to multiply by 2 √1 minus x and divide by 2 √1 minus x. Notice the numerator simplifies to what? Just 2 times 1 minus x. And this other side already has that on its denominator, so we just need that -x. And I'll distribute that 2 through. Distribute the 2, you get 2 minus 2x. 2 minus 2x minus another x gives us 2 minus 3x. Any questions about, well, all we did so far was simplify the derivative. We haven't set it equal to 0 yet, but any questions about simplifying? You could have set it equal to 0 here and, gone through that algebra. But here, we need to set this equal to 0. It's 0 when the top equals 0, which is when x equals 2/3. And it's undefined when the bottom equals 0, which is when x equals 1. And notice 1's already part of our interval, so that's not adding more to this. Any questions so far? So right now, we've found all of the values we need to consider, and we just have to consider the function at them now. And pick out the largest and pick out the smallest. So our endpoints are -1 and 1, and we need also 2/3. Because 2/3 is within that interval. Evaluated at 1, what do you get? 1 times 0, which is 0. Evaluated at -1, you get -1 root 1 plus 1, which is -√2. Evaluated at 2/3, what do you get? Two-thirds root 1 minus 2/3, so under that square root you have a 1/3. 2/3 root 1/3, which, man, root 1 really shouldn't be written, but if you left it like that, that's fine. I guess I'll just write it like that. Now we have all these square roots here. So it might not be immediately obvious which one's largest, which one's smallest, but notice we have 0, a negative number, and a positive number. So the negative is the smallest, and the positive is the largest. Any questions about that one? Okay, part C, we have a trig function now. -π/4 to 3π/4. Well, again, we're going to need the derivative. We're going to need where it's 0. We're going to need where it's undefined. This derivative is sine, so that's always defined. But here, what's our derivative? Well, derivative of cosine is negative sine. So the negatives cancel. That's nice. But we need also to multiply by the derivative of 2x, which is 2. And here we want to set this equal to 0. And conveniently, we have this nice restriction on our domain, which is nice for solving a trig function. Set that equal to 0, it's the same as what? Sine of 2x equals 0. Well, how can we solve this? Where is sine equal to 0? Sine is what? Sine is the y value. Y value is 0 over here. Y value is 0 over here. So we will have a few different equations to solve here. But all we need are x values within this interval. So there aren't going to be that many we have to deal with. So first, if the inside is angle 0, then sine of that will be 0. So set that equal to 0. You get x equals 0, which is within that interval. So angle 0 must be considered. Angle pi. If the inside equals pi, then sine of that will be 0. So set the inside equal to pi, and we get pi over 2, which is also within that interval. What if you went all the way around to 2 pi? What if you went all the way around to 2 pi? Well, you get x equals pi, not in that interval, so we don't have to consider that. And what if you went the opposite direction? You went to negative pi, well, you get x equals negative pi over 2, also not in that interval. So you don't need to consider that either. but we do need to consider these x values because they are within that interval. So we have, oh, and that's never undefined because it's sine. So we have these two x values and our two endpoint values. And I always like writing them in order. And we need to evaluate our original function at these angles. So what do we get? Well, we have negative cosine of negative pi over 2. And we'll simplify that. We have negative cosine of 0. And cosine of 2 times the angle. We have cosine pi over 2 times 2. Negative. How did I drop that negative? Negative cosine of 2 times pi over 2, which is pi. And here, 2 times 3/4 is 3/2. So we have all of these trig functions to consider. Notice all of our angles are on the unit circle. Cosine of 0 is 1. So that's -1. Cosine of pi over 2, well, we don't need cosine of pi over 2. Cosine of pi is -1. The negatives cancel. Cosine of 3 pi over 2 is 0. And cosine of negative pi over 2 also 0. So the smallest is the minimum. The largest is the maximum. So are there any questions about this one? This one there was a good deal to consider. So any questions about this? So we have a test in what, 12 days? We've covered most of what's on the test. Next week, there are actually only 2 topics we're considering. So this weekend, you could get a pretty good idea of, how you should go about attacking studying for the test. But there are going to be 2 more topics next week. One medium size, one, let's say they're both medium sized. The lecture times will be a little different, but their topic size, I would consider both about medium. So there is a homework assignment this weekend. So do try to get that in by Monday, but also do try to enjoy your weekend. The weather is supposed to be reasonably nice.